Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this lecture we are going to solve problem 11.5 from the chapter 11 Rotodynamic Machinery, Applied Thermodynamics by Eastop and McConkey. The statement of the problem is the first stage of a turbine is a 2-row velocity compounded wheel. Steam at 40 bar and 400 degrees centigrade is expanded in the nozzles to 15 bar and has a velocity at discharge of 700 meter per second. The inlet velocity to the stage is negligible. The relevant exit angles are: nozzle angle is 18 degree, first row blades 21 degree, fixed blades 26.5 degree, second row blades 35 degree. Take the blade velocity coefficient K for all blades as 0.9. The mean diameter of the blading is 750 millimeter and the turbine shaft speed is 3000 revolution per minute. Draw the velocity diagram for this wheel and calculate two things: the diagram efficiency, also the stage efficiency. So first of all, we will extract the information from this statement. First, we have given the initial pressure of the steam, that is P1 40 bar, and temperature T1 is 400 degrees centigrade. After expansion, its pressure drops and it becomes 15 bar. Then the velocity at the discharge of the nozzle is 700 meter per second, that is the absolute velocity at inlet for stage 1, 700 meter per second. The nozzle angle is 18 degree. Blade angle for the first row is 21 degree. Blade angle for the second row is 35 degree, that is beta E2, and for second stage the inlet nozzle angles is 26.5 degree. Similarly, the value of D is 750 millimeter or 0.75 meter. The speed of the shaft of the turbine is 3000 revolution per minute. We have to find two things. One is diagram efficiency and second is stage efficiency. This is the velocity triangles for this 11.5 problem. We are familiar with these triangles. Problem 11.4 was also about the velocity compounded to 2-row velocity compounded turbine. So I hope these terms will be clear. We are directly going to the solution of this problem. After sketching the velocity triangles, there are two methods basically to solve this problem. One, to draw the velocity triangles to the scale and find it graphically. Second, to solve this problem, analytical or trigonometric method is used to solve it. The latter method is more accurate and we can find the accurate values from the second method, that is the analytical method. Our approach in this problem is to solve this to use the analytical method. So first of all, we will find the blade speed, that is R omega or R 2 pi n by 60. So R is nothing but d by 2. We can write it like this: 0.75 by 2 into 2 pi n is 3000 divided by 60. So these two will cancel. So simplifying this, we get the value of blade velocity, that is 117.8 meter per second. Now it has given that CAI1 is 700 meter per second. So to find other missing velocities, we can use cosine law or law of cosine. So for that, we can write from the first row triangle that CRI1 square is equal to CAI1 square plus CB square minus 2 CAI1 CB cos alpha I1. So now putting the values, we will find the value of CRI1. So CRI1 square is equal to 700 square plus CB is 117.8 square minus 2 into 700 into 117.8 cos alpha I1 is 21 degree. Cos alpha I1 is 18 degree. So replacing it by, from here alpha I1 is 18 degree. So simplifying this, we get the value of CRI1, that is 589.1 meter per second. Also, to find the value of CRE1, which is the relative velocity with respect to the blade at exit, for that blade velocity coefficient will be multiplied with the CRI1. So K is 0.9 and CRI1 is 589.1 meter per second. So multiplying this, we get 530.2 meter per second. So this is the value of CRE1. Now to find the value of delta CW1 from the first row, so for that we can write that 700 cos of 18 degree from the velocity triangle minus 117.8, which is the blade velocity, plus 530 point, this is the value, 530.2 cos of 21 degree. So simplifying this, we get the value of delta CW1 and the value of delta CW1 comes out 1042.9 meter per second. Also, to find the value of CAE1, so for that again we can write from the velocity triangle that CAE1 square is equal to CRE1 sine 21 square plus CRE1 cos of 21 degree minus CB whole square. So simplifying this, we get the value of CAE1 is equal to 422.3 meter per second. So this is the value of absolute velocity at exit for first row. Similarly, to find the value of CAI2, that is equal to 0.9 into CAE1. K, this is the value of K, which is blade velocity coefficient. So 0.9 into CAE1 is 422.3 meter per second. So we get the value of CAI2, which comes out 380.1 meter per second. So this is the value of CAI2. Now further we can write again from the triangles CRI2 square equal to CAI2 sine 26.5 whole square plus CAI2 cos of 26.5 degree minus CB whole square. So solving it for CRI2, putting the values, we get the value of CRI2 and it comes out 279.7 meter per second. Further, to find the value of CRE2, for that again using the blade velocity coefficient, multiplying it with CRI2, so 0.9 into 279.7. So the value of CRE2 comes out 251.7 meter per second. So this is the value of CRE2. E2. Further, now we can write the value of delta CW2, and it is equal to CAI2 cos of 26.5 degree minus CB plus CRE2 cos of 35 degree. So solving it, putting the values, we get the value which comes out 428.6 meter per second. So this is the value of delta CW2. Now it's very easy to find the diagram efficiency. So this is the part 1 of the problem. To find diagram efficiency is equal to delta CW1, which is 1042.9 meter per second, plus delta CW2 is 428.6 meter per second, into blade speed, which is 117.8 meter per second, and multiplying it with 2, because the input energy is the kinetic energy, and that is CAI square, which is 700. So simplifying this, we get the diagram efficiency value, which is 70.8%. Now to find the value of stage efficiency, so stage efficiency is nothing but it is the ratio of work output divided by the enthalpy drop, which is H1 minus H2S in this case. So we can write the work output from here, delta CW1 plus delta CW2 into blade speed. We get the work output from this. But to find the value of H1 and H2S, we will use the steam conditions at inlet. So to find H1 from the steam tables at 40 bar and 400 degrees centigrade, we will visit steam tables. So from there we can note the values of enthalpy. So at the given condition, the value of H1 is 3214 kilojoule per kilogram, and the value of specific entropy at these conditions is 6.769 kilojoule per kilogram per Kelvin. So to find the value of H2S, for this the value of H2S is isentropic value, means entropy will remain constant. So for H2, the value of H2 is same just like S1, which is 6.769 69 kilojoule per kilogram per Kelvin. So at this, and the value of pressure is from here, P2 is 15 bar. So at pressure 15 bar and entropy is 2 is 6.769 kilojoule per kilogram per Kelvin. So the value of H2 is from the steam tables is 2956.8 kilojoule per kilogram. So now to find the stage efficiency, for that we can write the expression, that is the work output, which is delta CW1 plus delta CW2 into blade speed divided by H1 minus H2S. So putting the values, delta CW1 is 1042.9 plus delta CW2 is 428.6 and the value of CB is 117.8 meter per second divided by the value of H1 is 3214 minus the value of H2 is 2956.8 kilojoule per kilogram. So to convert kilojoule per kilogram into joule per kilogram, we will multiply 10 raised to power 3 or 1000 with this figure. So the value of stage efficiency calculated from here comes out 67.4%. So this is the required value of stage efficiency. We found the values of diagram efficiency and stage efficiency which was required in this problem. So this is the overall solution of problem 11.5. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.